For this potentiometric titration, we have a number of different data points we need to get situated before we can actually start our calculation. First, let's identify the anode and the cathode. The anode here is going to be the saturated calomel electrode because that is what is attached to the negative side of the potentiometer. And that has a standard potential of 0.241 volts. The cathode is then going to be the silver. We have a silver wire, we have silver in solution. So the cathode is going to be reduction of silver, and it looks like this. Now that cathode has a standard reduction potential of 0.799 volts. So now let's have a look. What is the titration equation? I didn't mean to erase that. What is the titration equation that is occurring? We have silver, or silver ion, being reacted with bromide anion in order to form silver bromide. Now, silver bromide's KSP is 5.0 times 10 to the negative 13. Remember, when you have a KSP, what you're showing is the solid being in equilibrium with its pieces, with its ions. So remember, this is the way that a KSP is written, not this way. Well, that'll come into effect later. So now we know we have a titration. Let's figure out where that equivalence volume is because we have three different ways that we can handle this data. So we're going to start with the volume of the silver because that's what we're given. We're given this volume. So we have 10 milliliters of our silver ion, and it has a concentration of 0.0500 moles of silver ion per liter. Now the stoichiometry of this is 1:1. So for every 1 mole of silver ion, we need 1 mole of bromide to react. Our bromide solution has a concentration of 0.0250 moles per liter. So this is going to give us our equivalent volume. And when you do this calculation, and what I mean by that is we're going to multiply everything in the denominator and divide it by everything in the numerator, you should end up with a volume of 0.0200 liters of the sodium bromide. Now that is 20 milliliters. That is our equivalence volume. So our equivalence volume is here. So we have before equivalence, at equivalence, and then after equivalence. So we're going to work all three of our calculations. Now this is all great, but what do we need in order to find that cell voltage? Well, we're going to use our Nernst equation. So we're going to take E of the cathode and we're going to subtract the E of the anode. Now the E of the anode is standard. It's a saturated calomel electrode, so we don't have to worry about that. But the E of the cathode is what's going to vary, and it's going to vary based on the concentration of the silver. So the E of the cathode is going to be the standard reduction potential, 0.799, minus our constant, 0.05916 over N, the number of electrons that are transferred, and there is one electron transferred, and that is going to be multiplied by the log of our Q value. Now our Q value this is of our reduction here, the equation that occurs at the cathode. So this silver is a solid. This is the only part that is in our Q value. So it's the concentration of the silver ion. So that is the E of our cathode. And then from that, we subtract the E of our anode, which is our saturated calomel electrode at 0.241 volts. So before the equivalence point, we need to calculate this silver. Now, the concentration of this silver is going to be dependent before the equivalence point on the excess silver in solution. So we need to calculate the moles. How many moles of silver are in that solution to start with? Well, we take our volume and we multiply it by our concentration, and we get 0.00 0.05 moles of silver. So how many moles of bromide are we adding? Well, for the bromide, we have 10 milliliters as well, because that's what's given right here, and that's the volume of my bromine. This V, I find the use of V's to be inconsistent because V is voltage, but V is also volume. So you'll have to watch out for that. Just make sure you're paying attention to the units. So 0.0100 liters of the bromide solution. The bromide solution has a concentration of 0.0250 moles per liter. So we have 0.000250 moles of bromide. Now, according to our titration equation here, for every 1 mole of silver, we use 1 mole of bromine. Well, this is our limiting amount of moles. So I'm going to subtract the moles of bromine from the moles of silver, and that's going to give me the excess moles of silver. And that is 0.000250 moles of excess silver. So I need to take that and I need to divide that by the total volume. So the total volume at this point, we started with 10 milliliters of our sample, and now we have added 10 milliliters of bromine. So we have a total of 20 milliliters, 0.0200 liters. And I get a concentration. So this is the concentration of the silver at this point in the titration. The concentration of the silver is 0.0125 molar. So now all I have to do is take this concentration that I've just calculated and put it into my equation. And when I do that, I get the E of the cell at this point is going to be 0.445 volts. So just to keep everything straight, I'm going to keep this table up here, and on a test or something, I would expect an easy way to tell what your answers are. So I would expect a table like this to be provided so that you could fill it in and tell me what your answers are. So before the equivalence point, we are dependent on the excess silver. Now at the equivalence point, we have taken all of those moles, so our 0.12350 moles of silver, and they have been matched with the same number of moles of bromide. Bromide in order to make 0.000500 moles of our solid. So now the concentration of the silver is dependent on how much of that solid forms its ions. And that's where the KSP comes in. So we have some amount of solid here. We don't know, it doesn't end up in our Q. And it's going to shift some amount X of our ion. And so now we set up our KSP. So the KSP is equal to 5.0 times 10 to the negative 13, and that's equal to X squared. That's the concentration of each of my ions multiplied together. So X is going to be equal to the concentration of the silver ion, and in this case, it's going to be the KSP, the square root of the KSP, which is going to be 7.07, and it continues, leave it in your calculator, times 10 to the negative 7 molar. So now that becomes the pink value that goes into the E equation. So again, the E of the cell is going to be the E of the cathode, which is 0.799 minus 0.5916 divided by 1 times the log log now of 1 over this value, 7.07 that's in your calculator. Then you're going to subtract the E of the anode. So that is the saturated calomel electrode, 1.41 volts. So the E of the cell at this point, you should be getting 0.194 volts. So now we are after the equivalence point. Now we are at 30 milliliters. And the concentration of the silver is still what we're after. And the concentration of the silver is still dependent on that KSP. So we have taken and converted a whole lot of stuff into silver bromide. And the concentration of the silver is still going to be dependent on the KSP, but this time we have an excess of bromide. So we need to know how much is our excess of bromide. Well, it's equivalent to 10 milliliters of our bromide solution, 0.0250 over L. Now you can do this by subtraction as well. I'm just showing you a different way. If this way doesn't make any sense to you, use the way that is presented earlier in the writing. So we have this many moles of bromide in excess, but we don't need the moles, we need the concentration. So we take this concentration and we divide it by the total volume. The total volume at this point is 40 milliliters. So we get those 40 milliliters by taking, well, I'm not gonna be able to see that color, by taking the 10 milliliters here and adding it to the 30 milliliters here. That's how we get our total volume. 0.40. So the concentration of our bromide is then 6.25 times 10 to the negative third. So that plus some value X that I don't know, the concentration of my silver is still going to be X, and I can set up my KSP. So the KSP is going to be 5.0 times 10 to the negative 13, and that's going to be equal to X times 6.25 times 10 to the negative third plus X. Now, this is one of those cases we can simplify because this X is just going to be insignificant compared to the initial concentration. So the X value then is fairly easily calculated, 5.0 times 10 to the negative 13 divided by 6.25 times 10 to the negative third. And you should get an X value of 8.0 times 10 to the negative 11, and that is molar. Now that becomes the pink silver concentration. So that gets fed into our Nernstian equation, and you should get an E of the cell value of negative 0.039 volts. So you can see the potential, the cell potential changes dramatically based on where you are in the titration.